Hidden life beneath our feet. The secret world of microbial ecosystems. Beneath our feet lies a secret world teeming with life, hidden in the darkest depths of the earth. What if I told you that the very rocks we consider lifeless are actually fueling a bustling underground ecosystem? It sounds like science fiction, but recent research has uncovered a fascinating truth. Earthquakes, often seen as destructive forces, are secretly nurturing microbial life deep within the Earth's crust. But here's where it gets even more intriguing. This phenomenon might not be unique to our planet. In a groundbreaking study, scientists from the Guangzhou Institute of Geochemistry, GIKAS, have revealed that when rocks fracture during seismic events, they release a powerful cocktail of hydrogen and oxidants. These chemicals, generated by the breakdown of minerals like quartz and basalt, act as an energy source for microbes thriving in the deep biosphere. Led by Professors He Hongping and Zhu Jiangxi, the team simulated earthquake conditions and discovered that the energy produced during these events is staggering. According to Xiao Wu, the study's lead author, the hydrogen released during rock fracturing is up to 100,000 times greater than any other known natural process. This energy bonanza transforms fault lines into thriving microbial oases, far removed from the sun's reach. And this is the part most people miss. The deep biosphere, hidden beneath the bedrock, accounts for about 15% of Earth's total biomass. For billions of years, tectonic activity and even minor quakes have fractured rocks, creating environments rich in reactive surfaces. These fractured rocks, infused with peroxy bonds, release energy when disturbed, akin to flipping millions of microscopic switches simultaneously. In just 4 hours of simulated fault movement, the researchers generated up to 160 micromoles of hydrogen, far surpassing the energy output from processes like serpentinization. Over time, this energy sustains dense microbial biofilms, with some microbes surviving on as little as 10 to the power of 12 watts per cell. Imagine, a single earthquake can release enough energy to power millions of these microscopic organisms, turning shattered rock zones into temporary nutrient hotspots. But hydrogen alone isn't enough to sustain life. It needs an electron acceptor. Here's where it gets controversial. The study highlights the role of ion cycling in this underground ecosystem. Reactive hydrogen atoms reduce ferric ion, Feq+, to ferrous ion, Fe2+, while hydrogen peroxide reverses this process, creating a self-sustaining redox cycle. This allows microbes to extract energy from iron, essentially feeding off the rusting process. Experiments on granite samples confirmed that microbes can thrive by transferring electrons from iron within rocks. Over time, slow weathering and chemical mixing stabilize the initial energy spike, enabling microbial colonies to establish and expand. Borehole samples from the Canadian Shield have shown ongoing ion oxidation and reduction over years, suggesting that this rock fracture chemistry is a long-term energy source for deep life. Could this mean there's more life beneath our feet than we ever imagined? Earth's tectonic network might be dotted with chemical hotspots, creating habitable zones in the crust far more extensive than previously thought. But the implications don't stop there. This research reshapes our search for life beyond Earth. On worlds like Mars, Europa, or Enceladus, where brittle crusts experience stress from impacts, tidal forces, or cooling, similar geochemical processes could be occurring. Mars rovers have already detected iron minerals capable of redox cycling, and orbital images reveal vast networks of surface cracks. This study provides a roadmap for future missions, suggesting that instruments detecting hydrogen, methane, or shifting ion states could pinpoint potential habitats in these fracture zones. Instead of focusing on surface oases, perhaps the best places to search for Martian life are the dark, cracked veins beneath the surface. Back on Earth, glaciers offer a striking parallel. As they climb through the basalt, they release hydrogen, fueling microbes in subglacial lakes. Whether through tectonics, landslides, or ice movement, mechanical stress appears to be a universal driver of underground ecosystems. This raises a thought-provoking question. If life can thrive in such extreme, energy-rich environments on Earth, could similar processes be sustaining life on other planets? What do you think? Are we on the brink of discovering hidden biospheres across the cosmos? Or is Earth's underground life a unique anomaly? Let's discuss in the comments. How microorganisms survive deep underground without sunlight, tectonic faults, and Earth's hidden life. Imagine a world beneath our feet, thriving without a single ray of sunlight. This isn't science fiction, it's a groundbreaking reality uncovered by Chinese scientists. A recent study published in Science Advances has shattered the long-held belief that all life on Earth is sun-dependent, revealing how microorganisms survive deep within the Earth's crust. Unveiling the mystery. Led by Professors He Hongping and Zhu Jianxi from the Guangzhou Institute of Geochemistry, Chinese Academy of Sciences, the research delves into the enigmatic processes occurring in tectonic fault zones. These zones, where the Earth's crust shifts and fractures, are hotbeds of activity. The scientists discovered that these fractures release free radicals, tiny, highly reactive particles that break down water molecules into hydrogen and hydrogen peroxide. This breakdown creates a redox gradient, a key player in the survival of these microorganisms. The chemistry of survival. But here's where it gets fascinating. This redox gradient triggers chemical reactions involving iron, which exists in two states, ferrous, Fe2+, and ferric, Fe3+. These ion transitions support essential biochemical cycles for carbon, nitrogen, and sulfur, providing the microorganisms with the necessary substances for metabolism. Essentially, this allows them to thrive in environments devoid of sunlight and organic compounds. Tectonic faults, nature's power generators. A startling revelation from the study is the role of tectonic faults, especially during earthquakes. These faults can produce an astonishing amount of hydrogen, up to 100,000 times more than other known mechanisms like serpentinization or radiolysis. This makes fault zones a vital energy source for the subsurface biosphere, enabling microorganisms to flourish several kilometers below the surface in extreme conditions. Redefining our understanding. This research revolutionizes our comprehension of Earth's subsurface biosphere. Previously, it was thought that life deep underground relied on limited energy sources, such as surface organic matter seepage or rare geochemical processes. Now, it's clear that tectonic faults provide a powerful and stable energy source, sustaining complex microbial ecosystems in harsh, light-deprived environments. Their implications for astrobiology. And this is the part most people miss. The findings have profound implications for astrobiology. The conditions created by tectonic activity on Earth could mirror those on other rocky planets, like Mars or the moons of Jupiter and Saturn. The hydrogen and redox reactions identified might be crucial in the search for life in subsurface oceans or rock formations on these celestial bodies. Looking ahead, the authors stress that their work paves the way for further exploration of underground life. Future research aims to explore how different tectonic faults impact microbial communities and identify the most resilient microorganisms. Additionally, simulating similar processes on other planets could provide deeper insights into the potential for extraterrestrial life. A new chapter in science. This discovery underscores the significance of interdisciplinary research, blending geochemistry, microbiology, and planetary science. Understanding life's resilience in Earth's extreme environments could be the key to unlocking the secrets of biospheres beyond our planet. Conclusion. In summary, the groundbreaking work by Chinese scientists redefines our understanding of life deep within the Earth. Tectonic faults, by generating hydrogen and hydrogen peroxide, offer microorganisms a lifeline, enabling their survival without sunlight. This not only broadens our knowledge of the subsurface biosphere, but also opens new doors in the quest for life in the universe. It challenges us to reconsider the resilience and ubiquity of life, inspiring further exploration of both our planet and the cosmos. So, what do you think? Could life be more widespread and resilient than we've ever imagined? Share your thoughts and join the conversation below. Discover how cracked rocks power life deep on Earth and beyond. Deep beneath the Earth's surface, where sunlight never reaches, microbes thrive on the energy released from cracked rocks. A groundbreaking study reveals that this energy comes from hydrogen and oxidants generated during fault movements, challenging the age-old belief that all life depends on sunlight. Researchers at the Guangzhou Institute of Geochemistry mimicked earthquakes in high-pressure experiments and observed free radicals splitting water into hydrogen gas and hydrogen peroxide. The production of hydrogen driven by earthquake-related faulting was found to be up to 100,000 times greater than other known pathways. Despite sunlight fading within a few yards of bedrock, the deep biosphere hosts around 15% of Earth's biomass, primarily bacteria and archaea. Billions of years of plate movements and daily microquakes provide this hidden ecosystem with freshly fractured surfaces, creating reactive radicals that split water into usable energy for microbes. The deep crust's abundance of silicate grains with hidden peroxy bonds makes each seismic slip highly impactful, converting approximately 0.0015% of mechanical energy into chemical energy, enough to sustain underground microbes between major quakes. But here's where it gets controversial. Hydrogen alone isn't sufficient for life. An electron acceptor is also necessary. The experiments demonstrated that reactive hydrogen atoms easily convert ferric iron back into ferrous iron, while hydrogen peroxide turns ferrous iron back into ferric iron in nearby pores, establishing a self-sustaining ion cycle that some bacteria use for energy and carbon cycle support. This study suggests that self-renewing redox interfaces may be present in fault networks worldwide, greatly expanding habitable volume. Evidence from deep Canadian field boreholes shows iron shifting between forms over several years, indicating that underground microbes remain active by utilizing hydrogen from fractured rock. These findings highlight the potential for similar chemistry beneath the surfaces of Mars, Europa, and Enceladus. Mars orbiters have already mapped extensive rock cracks, and rovers have discovered types of iron capable of switching between two forms. Tools detecting hydrogen, methane, or ion changes could identify signs of life in seemingly barren landscapes. Back on Earth, this research broadens our understanding of the deep biosphere, demonstrating that tectonic stirrings, glacier creep, and landslide grinding all contribute to underground food chains. Life, once again, proves its resilience and adaptability in the face of adversity.